Welcome to the Crazy Hat Chemist. So here's another video in periodicity, so let's get moving. Bam! So today we're talking about atomic radius of atoms. So first we need to give a definition of what we mean by the radius of an atom. So the atomic radius is defined as 1/2 the distance between the centers of two identical atoms that are covalently bonded. Okay, so here's a little diagram of two atoms. I've detailed out the nuclei of those two atoms and the distance between those two nuclei, and then 1/2 of that distance. So 1/2 of that distance is the atomic radius. So that's what we're talking about. Okay. All right. So for main group elements, that is S and P block elements, the atomic radius generally increases in a group with increasing principal quantum number n. That is, that the size increases going down a group. Okay? Additionally, within a period going from left to right, that is from left to right, the atomic radii decreases. Okay? So we're going to check both of these out on a graph and then also on the periodic table, and hopefully that will make sense and congeal this together for you. Okay, so here's a graph of atomic radius of the atoms versus atomic number. Notice that the atomic radius is in picometers. That's times 10 to the -12th of a meter. And then the atomic number is on the x-axis and the radius is on that y-axis right there. I'm going to highlight some certain sections on here so that you can really read this graph. So what I've outlined here are the group 1, the alkali metals. And you should see that I have lithium, sodium, potassium, rubidium, cesium, and francium highlighted out there for you. And here is group 2. That's beryllium, magnesium, calcium, strontium, barium, and radium, all there highlighted. Now, and here are the noble gases. So helium, neon, argon, krypton, xenon, and radon. So you should see that there's a straight line as you go through the group, and that is as you are going down the group, you should see that that line, as you increase in atomic number, then the radius gets larger, looking at that graph. And let's take a look at that again with group 1. So with group 1 that are highlighted in the black there, you should see that as you increase the atomic number, then the size increases as well. Now you should be asking yourself, the size increases going down a group with this characteristic here of increasing atomic number. But why is rubidium, cesium, and francium not on the line? So you should see that with group 1, or even if you were to look at the red highlighted sections in group 2, or even the noble gases, if you were to draw that blue straight line going straight up here, you would see a relatively the same kind of trend. And why is rubidium, cesium, and francium not on the line? The same question can be asked for group 2 with strontium, barium, and radium. And I'm hoping that you remember back to atomic structure, and you remember the rungs to the ladder and how they are not equally spaced. That is, the rungs on the inner part of that ladder that is closest to the nucleus, n equals 1, n equals 2, that's a large distance. And as you get further from the nucleus, those rungs to the ladder, the distance between the rungs is closer and closer and closer and closer. Okay, so that is why you see that tailing off. You should see lithium, sodium, potassium, then rubidium, because the rungs to the ladder are getting closer. Cesium, the rungs to the ladder are getting closer, and francium, that's why that graph kind of tails off there. I didn't show it right there, but that's, hopefully you can absolutely see that on there. Okay, I'm going to highlight another section here, and this is in the transition element region. And there are reasons why the transition elements generally form this V-like pattern there. Okay, and you should see that there's a size differential, and that also goes back to the atomic structure and orbital boxes, if you will. Many times it's the half-filled orbitals. Remember, if it's a D shell, for example, half-filled would be 5 electrons in there, and that's very low in energy. And then also, as you backfill those orbital box diagrams, then you backfill them, and then you have a subset of D shells that is relatively low in energy too. So there's a reason for that with the atomic radius as well. Okay, then the size decreases going across a period. Okay, that is from the right to the left, the size increases, but it decreases going across a period like potassium, and then so from the left to the right, the size decreases. Okay, that's the real rule there, is that the size decreases across a period going from left to right. Okay, all right. Now, I'm going to show you this on a periodic table. I have highlighted some of the elements and their sizes in picometers so that you can take a look at some of them. Those are just a selection of some of the atoms and their atomic size in picometers. So as you look at group 1 or any group, group 2, or even the noble gases or with the halogens, you should see as you go down a group, then the size increases. So for example, hydrogen is 37, lithium 152, sodium 186, potassium 227, etc. As you go down a group, the size increases. Furthermore, as you go across the period from right to left, the size also increases, or how, if you want to look at it, going from the left to the right, the size decreases. Okay? All right, and there are numbers on that periodic table for you to take a look at as well. Overall, that arrow is going down. So as that arrow goes down, that means francium is huge. Okay, and so as you go across that period and down, then you get larger and larger. That's why francium is very large. Okay, that was the first sizing there. And now I got a crazy hat. So I am the Mad Hatter. That would be a great name for the back of my t-shirt, would be the Mad Hatter. So why are Mad Hatters labeled as Mad Hatters? That's a good question. So a long time ago, hatters used to take the black felt hats and dip them in mercury, or maybe rub mercury on them. Now, they didn't wear any gloves or anything like that, and mercury is volatile. So Mad Hatters is that hatters became mad because the mercury would mess with their brain and they wouldn't be the same as what they used to be after a while. So that's why Mad as a Hatter, because the hatters would put mercury on felt hats to make them shiny so that people would want to buy them. If you like that video and you learned something, give me a thumbs up. Please subscribe to my YouTube channel. Pass on the word to other people who want to learn cool chemistry stuff with great explanations. See you later. Talk to you next time. Bye now.